guys, welcome back to the channel. I wanted to film a video getting more in depth on neural interfaces, and I want to explain one of the core tenets of how to build an electrical neural interface. This is the type of neural interface you see Neuralink building. It's the type that most researchers deal with to be able to record electrical signals from the brain, whether that be action potentials or other electrical oscillations, or stimulating electrical signals into the brain to be able to stimulate neurons and make them fire. And when you're building a neural interface like this, something that's very important is to have a low impedance value. And what impedance means is the sum of reactance and resistance. So that's like the total resistance to electrons moving in your circuit. You want to minimize that. And let me explain why. So first, let's take a look at stimulation, and then we'll take a look at recording. So when we're looking at stimulation, one of the most important constraints we have when stimulating neurons is we want to be efficiently allowing the current to get into the brain. And there's a few things here. First, tissue overheating. We cannot overheat the tissue in the brain. One of the biggest challenges with neural implants is you overheat the brain. And if the brain is overheated by 3 degrees Celsius, like that's not allowed by FDA standards, I think. But to be honest, like heating it even 1 degree Celsius, we don't know what will happen. We don't know the long-term implications. So it's super important to make sure we're not heating up the brain. And the second thing is power. A lot of these neural interfaces are powered by batteries, and charging them is a whole process in itself. So we want to make sure we can reduce the amount of energy we expend from batteries and not heat up the brain. So in order for both of those two things to happen, we need to reduce the thermal heat that's generated, which means reducing the resistance of the circuit. Now let's take a look at the other side, so recording. And when you're recording, what's the most important thing? It's your signal to noise ratio. You want a really good signal to noise ratio. That means a clear signal with a little bit of noise. One of the biggest types of noise you see in these electrical circuits is something called thermal noise or thermal Johnson noise. And thermal noise occurs in any circuit. Like even if you had wires connected without a battery source, there would still be thermal resistance if you were trying to record the current in that circuit because electrons are moving. And so what ends up happening in these brain implants when you're recording is that you can have such high thermal noise that it overpowers the signal that's generated from the neurons. So it's really important to reduce this thermal Johnson noise. So ultimately, when you pull these two together, it tells you that a strategy for combating this to make sure you have efficient current injection and efficient recording is to have a low impedance. So low impedance, when you take that out further, how do we do that in a circuit? We can either have low resistance and also high capacitance. So that leads us to one of our fundamentals of building a neural interface electrically. Low resistance, high capacitance. If you're interested, I can explain in a later video how to make that happen. Let me know. Anyways, subscribe, stay smiling. I'll see you later.